Hello, we are live. Hi, I'm Andrea Angela, and today we are looking at a paper on computer A-level computing on advanced theory, and the paper is the one on November 2016. Okay, let's start. Okay, so we have a bunch of questions about real numbers and how they stored. So the first question is represent the number 2.5 using the mantissa and exponent. And we use 12 bits for the mantissa and 4 bits for the exponent. So the idea of representing real numbers in the computer is that basically a number is written as a mantissa multiplied by 2 to a particular exponent, right? So that's basically what the number n is. So we are splitting the number in two components, okay? So if you think about 2.5, this is made of two parts, the integer parts and the fractional parts. A way to convert the number into a floating point is to, first of all, split the two parts, right? So this is 2 plus 0.5. Then you convert these decimal values in binary. So what is 2 as a binary representation is 1, 0. And what is 0.5 in a binary representation? It is 0.1. Why? Because 1 is the first digit after in the fractional part. That basically means 1/2. If you use decimal representation, for example, if you have a 0.1, 1 means 1 out of 1/10. But in a binary system, 0.1 means 1/2. Okay, 0.5. So that's exactly the conversion between the decimal value and the binary values. If you sum those two, the number becomes 10.1. Okay, but we are not quite there. We are not quite in the form of mantissa multiplied by 2 and the exponent. And the mantissa is always represented with a single digit as an integer. So you have always the dot after the first digit. So you either have 0 dot or you have 1 dot. So we are not quite in that state because we have 2 digits as the integer part. So we want to kind of move this move the dot in a way that you always start with 0 dot. And the reason is because positive numbers using a floating point representation always start with 0 dot, while negative numbers always start with 1 dot. Okay, so in order to have 0 dot, we need to move the dot, the dots 2 points to the left. So this means that we are going to have 1, 0, 1, like that. In order to have the same value, so in order to have 10.1 from 0.101, we need to multiply by 4. So we need to multiply by 2 per 0.1. I'm kind of mixing a bit decimal and binaries, but you get the idea. So sorry, 0.2. So this means that if we multiply by 2, we move the dot to the right of one position. So it's like in the decimal system, when you multiply by 10, you move the dot to right of one in one position. So it's the same approach. So basically now you've got the two parts. The first part, this one, that is the mantissa, and this part that is the exponent. So this should be represented as binary. It's 1, 0 basically. And we can actually then copy this into the various the two boxes. That is obviously adding the values 0 at the beginning that are like that. So the exponent is 1, 0. So this is going to be 1, 0, like that. And the mantissa is 0, 1, 0, 1. And then we can add a bunch of zeros that are not meaningful. Don't bring any value. And this is basically the representation of 2.5 using floating point representation. Excellent. So the next question is asking how to convert this number as a negative number. So when you want to do this kind of operation, you basically take the exponent is going to be always the same when you between a number with the same absolute value. What is changing is the mantissa. And the way to change is this to calculate the 2's complement of the mantissa. So I'm gonna copy the mantissa here for simplicity. Let me zoom out a bit. So I have 0.101 0000000. Okay, I need to do basically the 2 complement of this. That is of this. That is we need to first change all 0 to 1s and all 1s to 0. So that will become, let me do here, so it's going to be aligned. This will be 1.0, 1, 0, 1, 1, 1, 1, 1, 1, 1, 1. And then you need to add 1. Because this is the way you calculate the 2 complements. So this one is the 1's complement. And if you add 1, it becomes the 2 complement. And the result is, you can start from right, this becomes 0, 0, oops, 0, 0, oops, 0, 0, 0, a bunch of zeros. We have 3, 6, 8 zeros, 3, 6, 8, 0. Then we have a 1, that, right? And then we have a 1.1, 1.01. So let me align this for you to make it more sense. There we go. And this is basically what we want to add here in the answer. 1, 0, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0. When you want to calculate a negative number as a floating point number, you first calculate the positive number, okay? Then you basically get the mantissa and the exponent. And for the negative number will be the same exponent, but the 2's complement of the mantissa instead. That's how you can do this operation. So the next question is find the denary value for the following binary floating point number. Okay, so here we need to do the kind of the opposite approach. So we need to take the number 0.011, multiply by 2 to 11, right? So what this is? So this is the 11 is actually, let me convert this into decimal. So that means multiplying by 8 1, and that means moving the dot 3 position to the right. That will pretty much become 11. That is 1 1. That is the value in decimal is 3. That in decimal is 3. Okay. So the idea is that you take the mantissa's binary, then you move the dot based on the exponent. So the exponent is 3, so you need to move the dot right in 3 position. In this case, we are lucky because we get just an integer value, so we don't have any fractional part. So another possible approach of doing that instead is to actually take the value of each of these ones. Like for example, in the mantissa we have a 1 in the second position in the fractional part that correspond to 1/4, and then we have another one immediately after that correspond to 1/8. Okay, so you basically you immediately convert the mantissa to a decimal number, and then you do the same approach, multiply by 8. Then you get pretty much the same value. Okay, these are 2 different approaches, right? Either the first one or the second one, they both are good to get the full marks. I tend to prefer the first one, but it depends. It depends by your preferences. Right. So the next question is if the floating point number is actually normalized or not. In order to be normalized, a floating point number need to have the mantissa need to start with basically 2 different bits, 0.1 or 1.0. In this case, it's 0.0, as you can see here. So it's not normalized. Now, the reason is basically what I said, is that the first 2 bits should be different in order to be normalized. So justify the answer, why it's not normalized? Because the first 2 bits of the mantissa should be different, right? Either 0, 1 or 1, 0. Okay, so now the system changes so that you can allocate 8 bits to the mantissa and the exponent. And what is the effect on the numbers? So if you, instead of having 12 bits for the mantissa, use less bits, like in this case, what it means that you have less possible, the number of values that you can get is less. And this means that the accuracy is reduced. There will be more gaps between the values. So, and this is the answer. So the accuracy is reduced. But in addition to that, because now the exponent gets 8 bits, that is more than the 4 bits that we had before, it means that you can really increase the range of the values that you can represent, because bigger exponents means bigger numbers or lower numbers, right? So the range of values that you can, let's say the domain of values that are available is bigger. So the range is increased, but there's less accuracy. So basically, your points are spread across a bigger range. So this means that you have less accuracy to represent, numbers that are very close together. So the range is increased. Okay. So the next question is about compilers. So you need to draw lines to link each statement to the correct compilation stage. Okay. So the first statement is this stage removes any comments in the program source code. So one of the parts of the compilation stages is the lexical analysis that consists of basically taking the source code and create a list of tokens based on the programming language that your code is written into. And part of this process is actually removing anything that is not needed in order to generate the actual final machine code. So comments are certainly tokens that are not required by the compiler in order to actually do his work. So they actually are removed in this stage. So we can actually draw a line from here to here. The second is this stage could be ignored. Okay, so this is basically optimization. So optimization is something that a compiler does at the end that helps to produce the most optimized machine code possible. So it's definitely something that you can ignore, because the program will still work, but will not work as with the same performance. Will be a bit slower than an optimized version of the program. But it's not strictly required to optimize a program. But nowadays, it's always a good practice to turn it on, because compilers these days are very smart and they can produce code that is very efficient. So it's worth using it, but it's not a mandatory step. The next statement is this stage checks that the grammar of the program source code, and this is actually the syntax analysis. So this actually consists of taking the list of tokens and trying to build an abstract syntax tree. And if during the process of building a syntax tree there is a grammar error, will be actually notified. And the syntax analysis is actually all about that. So it's checking the syntax and building the syntax tree. So this connects to the syntax analysis. And the last point is that this stage produces a tokenized version of the program source code. As we already said, the lexical analysis is actually responsible for doing the tokenization of the program source code. We haven't touched the code generation because it's not relevant at this stage, but that's actually the part when actually the compiler generates the actual machine code at the end. Okay, the next question is a totally different thing. That is about the reverse polyth notation. So you know that we can represent expressions using the infix notation that we are used to from mathematics. So we have an expression a plus b multiplied by c minus d. We want to convert this into reverse Polish notation. So the idea of the reverse Polish notation is basically to, it's definitely not a human-friendly representation of an expression, but it's very useful for computer because it's very easy to parse. The idea is that you put an operand. You put let me type it here. You put the first operand, the second operand, so let me say operand, the operand 2, and then the operator. So basically, you always put the first two operands of a binary operation to the left, and then the operator stay to the right. While in the infix notation, the operator is always in the middle. While instead, if you have a unary operator like minus a, you have the operand 1 first, and then the operator. Okay, the operator is always at the end. Okay, so this means that you can actually, if you want to evaluate the expression, you can just scan through the list of operand and operators, and as soon as you reach an operator, you already have all the information you need in order to evaluate the expression. But we'll get there in the next questions. So here we need to convert this infix notation to the revert Polish notation. So as you can see here, we need to consider the operator precedence in order to build this. So what is the things that has the highest precedence in this case? Because we are using parentheses, a plus b is the most the things that need to be done first. So how we can convert that? We put the operator first, a, b, and then we put plus, right? So this is actually how to convert that. And then the next step is to do the C minus D, and that will be converted in C D minus, and then at the end you put the star, that is the other operator. Okay, and so if you think about that, it makes sense, because if you move from left to right, you first find the plus, and then you do A plus B. Then you move to the right, you find the minus, you do C minus D. Then you find the star, and you basically do the star of the two partial results. Okay. So the next one is similar. So you get a unary operator that is minus a. So you convert that into a minus, because obviously the operator must be at the end. Then you have a divided by b. So again, you invert the things. First the second operator, and then you put the operand b, and then you put the operators divided, and then you have by 4, and you need to do swap the two things again, 4 star, and then you have divided c minus d, but there are parentheses, so I need to do c minus d first. I do c d minus, and then I use divided, and that's actually how you can convert the infix notation to the RPN notation. Okay, so the next question is actually about evaluating an expression that is written using the RPN notation, and you are being given the value of some variables, and you need to actually produce the stack, the status of the stack during the evaluation. So when an interpreter evaluates an expression that is written in the RPN form, it's using a stack in order to keep the status of everything that is being found during the scan. But the nice thing is that with a single scan, you can actually evaluate an expression using the RPN. It's quite amazing, right? So the first step is already been done, and is putting 2 on the stack, and 2 is actually the value of x. So we analyzed x as the first token that we found. Okay, then there is w. So this means that when an operator is found, or a variable in this case, what actually you do is just push this value onto the stack. You can't really do nothing, because you don't really know what's the operator that you need to apply at this stage. So you still have the 2 at the bottom of the stack, but then you put w, and w value is 1. Okay, then you put z. So you still have a 2 and 1, and then you put z. The value of z is 4. Okay, so next you find the plus operator. Okay, at this point you find the operator, so you know that plus is a binary operator that requires two values, and you pick the 2 values from the top of the stack, that is 1 and 4, and you do the sum, and then you replace those 2 values. So you pop these 2 values and you replace with the result, and the result of 4 plus 1 is actually 5. 2 is still there because we haven't used 2 yet. Makes sense, right? So now at this stage we actually analyze plus. Now we see y. Y is 3, so in this case we just put 3 on top of the stack. Then we move on. We found minus, and now because we find minus, we do the same operation. And pay attention that the element at the top of the stack is the last operator. So you need to do 5 minus 3, not 3 minus 5. And 5 minus 3 is actually 2. Then we replace 3 and 5, and then 2 is still there. And then you move on, you find star, and star is actually the product, so 2 by 2 will be 4, and 4 will be left on the stack. And this is actually the end result of the expression. And this is actually how an interpreter can actually evaluate an RPN expression. So if you are keen to do this for fun, and actually for learning, it would be quite nice for you to try to write an interpreter like that using Python. So I definitely recommend you to give it a go. It's quite fun. And if you need any help, let me know. Then the next step is you have this expression here as an RPN expression. You want to convert it back to the infix notation. In order to do that, you need to basically do the opposite approach. So we need to find the first operator, that is plus, and then this will become y plus z. So let's try to do it in steps. So this will be x that will be replaced with y plus z, because it's the first, y plus z. I'm kind of mixing the things here. So the first one is y plus z. Okay, so we still have y, we still have minus, and we still have star. Okay, then what we have next, we find the next operator that we need to scan multiple times. The first time we scan, we find the first operator is plus, and we convert wz plus to the actual infix notation, that is w plus z. Then we scan again from the beginning, and we find minus. So now we actually do w plus z minus y. So we still have x. We have w plus z minus y. Then we still have star at the end. And then, as you can see, then the result will be x star y plus z minus y. That's actually the result. So in order to do the opposite, so converting from RPN expression into the infix notation, you need to do multiple scans, because now you don't have the luxury of the RPN expression where you can just do everything in a single scan, because in the infix notation, the priority of the order of the operators matters, and the parentheses need to be used in order to make sure that this is preserved. So that's what is the advantage of using the RPN expression to evaluate an expression. I already mentioned pretty much what's the advantage is that you can basically write an interpreter very easily. So you can do an evaluation easily, because there is no need to use brackets, and the evaluation can be done from left to right in a single scan. It's quite impressive. I mean, it's quite nice. Most of the calculator that you might use actually use this approach in order to do the evaluation of expressions. So basically, using RPN makes the evaluation very easy, because there is no need to use brackets. As you can see, all the brackets disappear when you have the RPN expression, because it's implicit what is the order of the evaluation, and the operator's evaluation can be done from left to right in a single scan, something like that. Okay, excellent. Move on. The next question is about paging for memory management in operating systems. So the main memory in an operating in a computer is divided in equal size blocks called page frames. That's actually an abstraction created by the operating system, and each process is divided into blocks of the same size called pages. And each process has a page table that is used to manage the pages of this process. So the whole idea is that the reason why paging has been introduced is because we wanted to be able to write programs that simulate having a memory that is called virtual memory, that is bigger than the real available memory, and use the disk or secondary storage mechanisms to actually back up the main memory. So the main memory usually at the time was maybe in the past was even more relevant. And so the main memory is not might be 1 gigabyte, but you still might want to be able to write programs that can address 5 gigabytes of RAM. So you write your code assuming that you have 4 gigabytes of RAM, even if in reality you don't have it, but the operating system does all the work for you to abstract this away from you when you code, and it's quite nice. But obviously, a page is necessary in order for the operating system to keep tracks which pages are actually loaded in memory and which one are not. So what you're asked to do is the page frame address entry for the page 2 is 245. As you can see, we have page 2 and the page frame address is 245. So state what the value of 245 could represent. As we said, as has been said here, the main memory is divided in blocks called page frames. So what could be a page frame address? Quite easily is pretty much the number of the frame. So starting from the frames, I assume will start from 0, and basically the number means the 245 is pretty much the 245th page frame from the start of the memory address. So that's pretty much it. It's kind of an index. It's kind of a number that represents the page frame. So it's basically the 245th page frame from the start of the memory address space. Okay, so page frame 0 will be the first one, then 1 will be the second one, and so on. So basically, this number means where is this page frame located in the main memory. And where these pages are stored when they are not in the main memory, this could be stored in secondary storage devices that typically are hard drives, SSD drives, or flash drives, anywhere. You can configure operating system, where this information can be stored, for example, but most of the time it's kind of hard drives or SSD drives these days. So these days we have 64 bits computers. They can address 2 to 64 bytes of memory. That is a huge amount of memory, and obviously our system don't have it, but we can simulate this address space thanks to the operating system virtual memory approach. It's quite nice. So now you've been asked, so when an instruction to be accessed is not present in the main memory, the page must be loaded into a page frame. So if all pages are currently in use, the content of a page need to be overwritten. So of course, it might be possible that a program is using more than the available memory. So, and in that case, if all the memory is filled and the program needs to access to a particular part of the memory that is not in the main memory, but is stored on the secondary storage, the page need to be loaded. The page frame need to be loaded, but you need to replace one of the current ones in order to be able to make it room for it. So there are different ways of doing this, different possible algorithms, and if you want to do this using the longest time, so you want to replace the page that has been in the main memory for the longest time, what kind of additional information you need in order to do that? You need to be able to kind of know the time when basically the page was actually loaded into memory, the first time it was actually accessed. So that's actually what you need. So you need the time when the page was loaded into memory, right? So if you have this information, you know which one is the page that with the longest time, so you can actually pick that, the operating system can pick that to replace it when it's needed. And so you need to fill the page with the new values for page 4. So if you remember from the previous page, page 4 presence flag was 0. That means that the page was not in main memory, and the page frame address was 0. That means it's kind of not used. So probably 0 will not be useful as a page frame address. We'll start from 1. It's kind of a null pointer. So it doesn't really matter what the value is here, because if the presence flag is 0, this value doesn't matter, but usually set to 0. So now 4 will actually contain some page frames. So we need to set that to 1. And what will be the address? That will be the address of the page that we decided to actually replace. And the questions say that we assume that page 5 is the one to be replaced. So page 5 address is, we can see from the table, page 5 address is 542. So the page frame address of the page 5 is 542, and that is what we need to put there, 542. And what would be the additional data? And we said that the time when it was loaded into memory, that could be what time is it? It's 2 November 2017, and now is 1838, something like that. So the actual time when the page was loaded could be anything similar like that. Okay, what instead if you want to replace the page that has been used the least? Okay, so the page that is being used the least, we want to replace it. So this means that we need to kind of count how many times a page is used by the operating system, by the software that runs on the machine. So we need to have sort of a counter, right? I would say we need a usage counter. Usage counter that basically is counting, counts the numbers of time the page is used. Okay. So every time the operating system touch, you need to use some software use a particular page, the usage counter will be increased. So you obviously would need to modify the code of the algorithms in order to do this. Okay, so now we do the same things. So now assume the page 3 is the one that will be swept into memory, and page 1 is the one to be replaced. So again, the page flag will be, the presence flag will be 1 because we actually have something in memory, and the frame address is the page 1, that is the one we replace. So what's the address of the page 1? We can see back in the table, page 1 address is 132. So we can fill it in, 132. And the additional data in this case is actually the number of time it is used. But because it's been actually loaded at this point in time, it's never been used yet. So it's not been used. So 0 will be the number to put in here because it's not been used. It's just been loaded. Okay. Okay, so the next question asking why using these two approaches could not be the best choice for efficient memory management. So the first one is the longest resident, means that if a page has been into my memory for a long time, it likely will be replaced by this approach. But that might means that actually the page is used a lot. It's always been there in the main memory. This means that it's been used since the beginning of the launch of the program, and this might be, some sort of static state that the program needs, and this is always used basically. So the problem is that with this approach is that basically a page is in memory for a long time, could mean that is used very frequently. So it is not the best strategy to remove it, right? So you might actually remove a page that is used very frequently. So not great. What about the least used? That's using this approach is quite obvious what can go wrong here, because you can think about if you just loaded a page, the usage counter of that page would be very low, and that's actually that means that as soon as another page needs to be swapped, the page that has been loaded now or recently will be the first one to go, and that's not great, right? Because if a page has been loaded into memory, it means that probably will be used pretty soon by the code, right? Probably it's going to be a local variable inside of a function, so you don't really want to swap it out. So I would say a page that was loaded recently has a low usage number, so it is likely that will be immediately replaced. So, and that's actually not a good thing. Nowadays, the operating system are quite clever. The best approach is usually to kind of trying to predict when the page will be, if the page will be used or not in the future. And the page that will be used more far away from in the future is probably the one that you want to replace. But also you can't predict the future. So the operating system basically use the past execution of a program in order to kind of predict how the program might actually work in the future. So if the program memory patterns is pretty much similar between runnings of the same programs, this is, could be a nice strategy to have, but obviously different operating systems implement different strategies, but probably not these two. Excellent. So the next question, number 4, is about binary logic in the circuits. So we want to create the table, the truth table of this logic circuits. So the first operation is an AND. So A is going to be the AND between X and Y, and the AND is basically 0 when there is at least 1 0 in the inputs, and the 1 when both the inputs are 1. And B instead is an OR operation. So that means there will be 1 when there is at least 1 1. So it will be 0 1 1 1. There we go. So what the name of this logic circuit? So it might not be immediately obvious, but you can see that B is pretty much the sum of X plus Y, and A is kind of the carry. It's kind of it's like doing the sum of 2 bits, where B is the sum of the 2 bits, and A is the carry. So that's actually, this logic circuit is called half-adder. That's also important for you to study it before the exam. And what they are usually called, so in this case, B is actually S, or you can call it actually the sum, and C is the carry. Oops. And C is actually in that. Apologize for that. Let's try again. Put this here. Now we got C and carry. All right. And explain why your answers are more appropriate for the A and B labels. That's quite obvious. Is that it's always good to use names that are closer to what the output or inputs are really hard. So I don't usually like to use A and B's for variables. So it's always better to use real names. So but basically is S is the sum of the addition of the 2 bits, and C is the carry of the addition of the 2 bits. Okay, so basically S and C make more sense because it's the initial letter of what they actually are. So the next step is actually to convert a logic circuit into a Boolean expression, and you can do that like this. So let's start from X. So X will be the AND between the first input of the AND is actually A. So A AND something between parentheses, we know, because it's actually a sub logic circuit that is not yet resolved. So then we need to do an OR here between A and B and C. So A and B plus C. That's basically how you convert this. You start from right and then you move to left. And then you need to simplify this expression, okay? So how we can do that? So let's use the distributed law here. So I can actually apply, so let me copy this here once again. The same expression. So here X will be A dot B plus A dot C. So I'm using the distributed, the distributed property of the dot product, and but I know that A by A is always A. So A and A is always A, because if he says 0, 0 dot 0 is 0. If he says is 1, 1 and 1 will be always 1. So I can actually remove that A dot A and convert into A. And then I can do A dot B plus A dot C. That means I can actually group it again. Oops. X equals A dot and B plus C. Okay, so the result is X equals A and B plus C. That's actually the simplified expression. So the main property that you had to use was actually A dot A equals A and the distributed law. Okay, so the next question is a question about networking. You need to actually know the names of all the various layers of the TCP/IP protocol suite. And this is actually the suite that is used actually for the internet, to send information across the internet. And the various layers are the application layer, that's how the application communicates. The transport layer, that is actually the TCP protocol. The internet layer is actually the IP protocol, and then there is the network layer, that is how the network communicate. That is Ethernet, and so on. And state how each of these layers is actually implemented. All of this is actually software, so there's nothing hardware here. The TCP protocol suite is all software, and software that is being created to basically allows application to send data across the internet towards another application in another location in the world. And this is actually all why the TCP protocol is being created. So the application can basically works like it's communicating directly with another application, and all of the layers below are completely abstracted away. And the transport layer is that the TCP layer, that means is responsible for doing the packet switching, and sending the various packets across the internet and assembling them together and so on. So giving making sure that the information arrive at the destination. The internet protocol instead is actually the actual routing. So the communication, the sending the various information to the destination host, and the networking layer is how is actually more of the low level information that basically is used to communicate between computers on the same network, local network. So like, for example, from your computer to your router. So this is no question asked in the paper. So the next step, you need to actually say, describe two tasks that the transport layer performs. So the transport layer, as I said, so I specifically is asking what the transport layer need to perform to ensure that the data is actually downloaded correctly. So let's focus on the part of the transport layer that does some sort of integrity check. And one of the things is the checksum. Calculate the checksum of the packet. So every time the packet is sent, there's also a checksum that is being sent. That's basically a number that is calculated by using the entire packet as an input. So if the checksum doesn't match at the destination, it means that the packet has been changed during the transmission, or by noise, or by a malicious user, for example. So calculate the checksum of the packet to verify that is valid, and ask for a retransmission if not. Right. So if the packet is not valid, we'll ask to the source to resend the packet. And another thing is actually reordering the packets in a way that the application can actually use access the data in order, because you know that the packets are sent across the internet in different following different paths. So it's possible that the packets do not arrive in order at the destination. So the transport layer is responsible for putting all the packets in order, so that the destination see the data in exactly the same order that the sender actually sent it. So check the packet destination port, and the port is a very important concept. So an application is kind of listening or talking through a particular port. So the way an application is represented using the TCP IP protocol is using the IP address that represents the machine, and the port represents the application running on the machine. Because you know that you have on a machine you can have multiple programs running. You could have Microsoft Word, you could have a PDF reader or anything like that. So it's a lot of, or your chat, Facebook, anything else. You can have a lot of software running on your machine, and each application is using a particular port in order to communicate and listen for it. So the port is the identifier of the application on a computer. So check the packet destination port to forward the message to the correct application. So this is another possible use. Sorry, I haven't. You need to pick two. Another one is actually reordering, like what I said, using the sequence number to reorder packet at the destination. That's a possible third answer. That's actually very important as well. So this is basically what the transport protocol does. So what is a protocol that can be used by process 1 and process 2. So process 1 is downloading a web page. So you probably know that this is HTTP or HTTPS. That's what actually the protocol used by your browser when you surf the internet. And when you actually want to download an email, the protocol uses POP3. Do not confuse that with SMTP. SMTP is only used for sending emails. So to receive emails, you need to use POP3. And then we have the last page. This is about security. We need to actually give a description of the type of malware. So malware that attaches itself to other programs is usually a virus. So that's basically what a virus is. Virus attaches itself to other executable code in order to spread across your computer. The malware that instead redirect the web browser to a fake website is called farming. And instead, an email that encourages the receiver to access a website and give, for example, the banking detail is phishing. Phishing. Okay, so phishing is basically writing an email that looks kind of legitimate when it is not, and farming is actually redirecting the web browser to a fake website that looks legitimate but is not. And the purpose might be the same, just to steal some data, but the naming is different. The phishing actually could also be, you could use phishing and farming together. Like you could send a fake email that when you click on the fake email, you go to a fake website, to input your information, right? So it's actually possible to do the same attacks together. And the last question is about cryptography. So Ben wants to send an highly confidential email to Maria so that only she can read it. So Ben wants to send a confidential information to Maria. And so you need to explain what plain text and ciphertext mean. So plain text is actually the message, the original message that Ben wants to send. So, so plain text is the original message. The ciphertext is actually the message that is encrypted. So is the original message encrypted? So is the encrypted version of the original message. Encrypted version of the original message. So how the use of asymmetric key cryptography ensures that Maria can read the email? So asymmetric key cryptography means that each of the person that want to communicate between each other have a public and a public-private key pairs. The private key is only known by the person. Excuse me. And the public key is known to everybody. In order to send a message to someone, you need to use the public key, and that's the person who's receiving the message. So this means that Ben needs to encrypt the email using Maria's public key, right? And the reason for this is because the only person that can actually decrypt the message is the one that has the private key, and only Maria can actually know the private key associated with her public key. So this guarantees the confidentiality. So basically, the idea is that Ben encrypt the email using Maria's public key, and Maria encrypts the email using her private key. Obviously, there is a process that need to take place in order for Ben to know what is the Maria's public key. But these two are this is an example of a correct answer. That's actually illustrate the main reason of public and private key infrastructure. And this is pretty much it. So thank you very much for watching. As always, any question, feel free to write me on Slack or send me an email to angela.andrea@gmail.com. Thank you.